All right, everybody, welcome back. Today, we're going to be talking about FP7. This is our factoring overview, so there's not going to be any new material today. Today's going to be kind of all about pulling back ideas that we have discussed in the past, right? So, first off, our directions are really kind of helpful in this because they tell us exactly what we want to do. Identify the greatest common factor. That's going to be what we are going to do first on all of these problems. We're always going to be looking for that greatest common factor, and then we're going to use that greatest common factor to write our expression in factored form. So when I look up here at problem number 1, the first thing I should be thinking is there any number that divides into 15 and 20? And of course the answer is 5. That means you can pull a 5 out of both of those. 15x divided by 5 would leave us with 3x, and 20 divided by 5 would leave us with 4. So I have 5 times 3x minus 4, which will be my final answer. Looking ahead to problem number 3, now we introduce another layer, right? This is just a big old onion ball of layers. The new piece that we add is that we have a squared and a. We have variables that are consistent between each of them. So we start the problem the same way. We say what number divides into 6 and also divides into 8? And that answer is, of course, 2. Now, if you notice, this one has 2 a's and this one has 1 a. Remember, you can pull out as many as the fewest one has, and then you just need to figure out what gets you back. So if I take 6a squared and I divide it by 2a, that would leave me with 3a. And if I take 8a and I divide it by 2a, that would leave me with just 4, right? Because 2a times 4 is equal to 8a, which makes this our final answer. Looking ahead to problem number 5. Now, when I come over here, we're thinking the same thing. What number goes into 8 and 20? Well, into 8, the biggest thing I think that goes into 8 and 20 would be a 4. Now, this one has 7 x's and this one has 9. Remember, you can always pull out as many as the fewest one has, so I'm going to pull out 7 of them. And then coming over here, now I just got to think, well, what would get me back? Well, 4 times 2 would equal the 8. And if I have 7 x's already, I wanted to have 9, so that means I just need 2 more right here. And then 4 times negative 5 equals that negative 20. And then I wanted 7 x's. It looks like I'm already getting 7 x's, so I don't need to worry about more, which means this will be my final answer. Moving on to problem number 6. Now we have 3 terms. So this process is still very much the same. What number can I pull out of each of these? Now, 6, I think, goes into each. You always want to get the biggest number if possible, so we're going to pull a 6 out because 6 does go into each. This one has 3 x's, this one has 2, this one has 1, so I can pull out 1x as well. Now, from here, you need to think what gets you back. So 6 times what is equal to 18? That's, of course, 3. I wanted to have 3 x's. I got 1 coming from the side, so I'm going to need 2 more right here. Moving on to the next term, 6 times 1 gets me back to 6. I wanted to have 2 x's. I have 1 coming from the side, so I need 1 more. And then last but not least, 6 times negative 7 equals 42. I wanted 1x. I'm getting 1x, so I don't need any more x's, which will make this my final answer. Moving ahead to problem number 9. Now, this one's kind of unique because one thing we notice is our leading term is negative. Remember, if you get a leading term that's negative, you need to pull that negative out. Now, 2 goes into each of these, so I'm going to pull out a negative 2 since that leading term was negative. There is no x in each of these quantities, right? This one is missing the x, so I can't pull any x's out. Now, negative 2 times 1 would get me back to negative 2, right? Or negative 2 divided by negative 2 is equal to a positive 1. And I'm going to have that x squared there. 20 divided by negative 2 would give us a negative 10. And negative 50 divided by negative 2 would be a positive 25. One thing that's important to notice is that notice how when I pull out that negative, what really happens is my signs flip on everything that's left. So this was a negative, positive, negative. Now it's a positive, negative, positive. My signs just flipped and went that other direction. Looking ahead to problem number 11. This one has, again, another negative as that leading term, so we're going to have to pull that out. So it looks like 3 goes into each of these numbers, so we're going to pull out a negative 3. Now, in this situation, each of them has an x, so I will be able to pull out an x as well. So what is left is what we should be thinking to ourselves. So if I pulled a 3x out of this term, I would just be left with 1x squared. 21 divided by a negative 3 would leave us with a negative 7. Now again, we started with 2 x's, you pull 1 out, you do still have 1 there. And negative 30 divided by a negative 3 would be a positive 10. And it looks like our x's should be good to go because I had 1, I pulled 1 out, we should be all set. So that wraps up the first page. Look at the second page. So in the second page, what it asks us to do is it asks us to factor as a product of binomials. What that means is this is when we came and we were doing that x method. Now remember, our general form for this, for the x, is going to be AC over b, and then this is ax, and we look for the bottom numbers that multiply to the top number and add to the bottom. Now remember, if you don't see any numbers, you can put them in. So this would be A, 13 is B, and 22 would be C. So 1 times 22 puts a 22 up top, 13 is going to go on the bottom. We're looking, or I'm sorry, I should then put my AX, so A is 1, so it's 1x and 1x here. We're looking for the two numbers that multiply to give us 22, that add to give us 13. Now, when I come over here and I start to think about this, 22 is kind of a unique problem, so let's just make a list here. So 22, so what numbers go into 22? Well, 1 goes in 22 times, 2 goes in 11 times, 3 doesn't go in, 4 doesn't go in, 5 doesn't go in, 6, 7, 8, 9, 10, 11. These are it. So it looks like this one's relatively easy. If it was a positive 2 and a positive 11, positive 2 times positive 11 would give us a positive 22. Positive 2 plus positive 11 would give us a positive 13. So remember, what we do is we look to see if our fractions can be reduced. These can't. So my answer is going to be 1x plus 2 and 1x plus 11. Let's go a little faster through the next one. On number 15, again, 1 times negative 13 puts a negative 13 up top, positive 12 on the bottom. Then we're going to have our 1x and our 1x. We're looking for two numbers that multiply to give us negative 13, that add to give us a positive 12. Now, since our multiply number is negative, that means one of my side numbers will have to be negative and the other one will have to be positive, so we can play around with our signs. I think this one's relatively easy because 13, the only thing I can think is 1 and 13. So let's just try to make the 1 negative and see if that works. Negative 1 times 13 would equal negative 13. Negative 1 plus 13 would equal a positive 12, so we picked the right one. So this is a negative 1 and a positive 13 here. Our numbers don't reduce in either one of the fractions, so my final answer will be 1x minus 1 and 1x plus 13. Great job. Moving on to problem number 17. 1 times 36 gives us a positive 36 up top. And then we're going to get a negative 12 on the bottom. We're going to have 1x and 1x here. Two numbers that multiply to give us a positive 36. So we're multiplying to be a positive and adding to be a negative. The only way that happens is if they're both negative, would be a negative 6 and a negative 6. They do multiply to give us a positive 36, and they do add to give us a negative 12. Our fractions don't reduce in either one of these situations, so my final answer will be 1x minus 6. That comes from this one. And then we're going to get 1x minus 6, which comes from that one, which makes this our final answer. Moving on to problem number 19. Looks like we got 3 of these left. So again, remember, to get your top number, it's always multiplying your A and your C together. So A is 3, C is 2, so we get 6 total. 7 is going to go on the bottom. We're going to have 3x here and 3x over and over. We need two numbers that multiply to be 6 that are going to add to give us 7. I believe those two numbers would be 6 and 1. And both of those could be positive here. Now, when I look at this, notice how this fraction, I can reduce it. 3 goes into 3 one time, 3 goes into 6 2 times. So I can make this into 1x plus 2 times 3x plus 1. And we're done. Look at 21. 21 gets weird, and the reason it's weird is because we're missing a term. We actually don't have our middle term, our b term, where we had the just x, right? So really right here we have 1x squared minus 81. This is your a and this is your c. We're missing the b. So what we can do in this situation is we can say plus 0 x, right? So just make b equal to 0 minus 81. Now again, when we do our x, our top number is still going to come from a times c. So 1 times negative 81 will be a minus 81. And then 0 is going to go on the bottom. We're going to have our 1x and our 1x on the sides. And now we need to think, what numbers multiply to give us negative 81 that add to give us 0? Well, how about a positive 9 and a negative 9? Neither of our fractions reduce here, so my final answer will be 1x plus 9, 1x plus 9, and 1x minus 9. Looks like we are on our last problem, so here we go. So looking at number 23. Now, number 23 is kind of a hard problem, and here's why. In order to do number 23, you've got to kind of start to realize a pattern. And here's the pattern. Now I'll show you number 24 just to make sure you're good with it too. But whenever this is a perfect square and this is a perfect square, what happens when we just have the two terms, this is normally when it shows up, is that as long as, I'm trying to think how I can explain this nicely to you. As long as those are perfect squares, then if you take the square root of each of those, the square root of 1 is 1. So we see that show up, and the square root of 81 is 9, and the only difference is 1 is positive, 1 is negative. Now, in this situation, this is a unique situation. We call it a difference of perfect squares. Whenever you have two numbers that are perfect squares and you are subtracting them, then what you can do is you can say, well, what's the square root of 36? Well, that's going to be 6, so you're going to put that in the front. And what's the square root of 25? Well, that's going to be 5, so you can put that in the back. And then all you need to do is add in the x's where you normally would have them, and you just make one positive and one negative. That's kind of a shortcut to help us factor these a little bit quicker. Here's another one. 49 and 81 are both perfect squares. So if I try to take the square root of both sides, the square root of 49 would be 7. We're going to put the x on that one. And then the square root of 81 is 9, so we'll put the 9 on that one, and we just make one positive and one negative, and that will give us our answer. Right? So on some problems, that's a nice little trick to use to make this a little bit easier to actually do. Thank you guys so much for watching the full video. If you have any questions, please don't hesitate to reach out. Thanks, everybody. Have a nice day.